So we'll continue from where we left. Okay, so in the previous session we were looking at the back propagation algorithm with the concept of momentum, and we also looked at what is called as the cost function, right? We defined the cost function first, and in say the cost function, we understood that the cost function is a specific function used in the machine learning to identify the ANN's error, right? So it's if you simply try to use the error in a straightforward way, right? So we can call that as E is equal to D minus Y. But the cost function is defined as the squared difference of the errors, as you can see in the equation number 1, and this is the plot. So the fundamental requirement of the cost function is that as the D minus Y or the error increases, the cost function is also should increase. That's what we can see here. Here the capital E represents the entropy based cost function, and there is another version of that depending upon whether the output is 1 or 0. Depending on that, right, whether the desired value is 1 or 0, we can actually change the we can bring a variety of what you call the entropy functions into picture. So that's what has been written in this particular equation, which is equation number 2. And we also have we check that how the plots are going to be, right? Whenever we try to plot, we observe that if the desired value is 1, we have a decreasing function like this with y, and if we have what you call d value becoming equal to 0, then we get an increasing function with y, right? In both the cases we can understand that the cost function increases, right, with the error. So then we wrote the steps required to be followed to implement what is called as the cost function, and how to implement the cost function based error back propagation. That's also all the steps we had considered in the previous session. So now our intention is to implement this, right, on the Matlab, right? So first let us consider the very similar data. Okay, first let me write the requirement over here, what we are going to do first. So now we will consider an example, and in this example this is example, we want to go for the MATLAB implementation of what is called as the cross entropy based the cost function, right? For this, let us assume the problem of the XOR function, and let us just recall what was the neural network structure we considered, right? So let me write the same neural network. This was the architecture of the neural network, right? We were considering all the way through since the beginning, right? So it's a multi-layer uh, neural network which has one input layer, four neurons in or the nodes in the hidden layer, and one output layer. So this is the neural network architecture, and let's use the similar training data, right? So the data set that we are going to use will be like this. Okay, so what is the class 0? Class 0 will have the following data sets. So that is 1 is 0, 0, 1, 0, and next one is 1, 1, 1, 0. These two data points correspond to the class 0, and the class 1 Okay, the class 1 is 0, 1, 1, 1, and this is 1, 0, 1, 1. Right, so this is the data. All right, so now let us shift to the MATLAB screen and let's write the code. All right, now let us do one thing. Let's create a function called the back propagation, and I'll give it a name as say this is back propagation, and I want to what we are trying to implement here is the cost function based on the cross entropy, right? So I'll write CEF, cost entropy function. All right, so that's what is the name, right? So actually it opens a new window, right? So let's start writing the code here. All right, so my first intention is that I'm writing a function, right? So let's follow the requirement of a function. This is function. I have to specify what outputs, right? This function is calculating the weight updation. So updated weights are W1 and W2. There are two weight matrices to be updated here, because we know that this particular neural network we consider has uh, two layers. One is a hidden layer and one is an output layer. So two layers are there. So two weights have to be optimized. So now let us consider the situation wherein I first write the name of the function. It should be same as the name of the file. So this is back propagation, CEF. Just mention what are the inputs, right? Inputs are the two weights W1, W2, the input vector X and the desired vector D. It will be passed on to this particular function. Okay, once it is done, so my next objective is, right, I define the alpha value. Alpha is equal to 8, 5. Okay, then let's define the number of classes over here, that is 4. Right, then I'll start with the for loop, right? For say I is equal to 1 to n, right? Take take the inputs one by one. So x is equal to capital X of the ith row, all the columns transpose. That is a x, and desired d is equal to d of I. So this gives you the desired vector for the given input x. Now once the x is given, our first step has to calculate the final output of the given neural network with the initialized weights, right, under consideration. So let's do the calculation now. So when the input goes to the first layer, it calculates the partial output called V1, right? So V1 should be equal to the weight W1 into the input, that is X. Once you get a V1, there is an activation function. It is a sigmoid function which calculates the output of the first layer, that is Y1. So Y1 has to be equal to my sigmoid of V1. So this generates the output of the first layer, right? That's a hidden layer. Now this is the output which acts like input for your next layer. So the next layer's output will be V. That has to be calculated by using the second set of weights, that is W2, multiplied by the output of the previous layer, which is Y1. All right. So the V is equal to W2 into Y1, and I should calculate the final output, that is Y should be equal to, right, once again my sigmoid function, my sigmoid of the output, that is a V partial output, to get a final output. Okay, so we got the complete output. Now once you have the output, we already know what is the desired value. So desired minus the that particular output value is going to give you an error. So let's calculate the error first. So that E is equal to, this is D minus Y. So it generates an error E. Then if you remember, right, what is the delta of the output? Delta of the output layer under this particular concept, uh, concept of the cost function using the entropy, right? It is nothing but you assign the delta, right? That the delta should be equal to what? Error itself, right? So delta is equal to E. This is the difference between the other techniques and this technique. Then you proceed further, calculate E1, right? So the error has to be calculated for the hidden layer, that is by using the weight of this layer, that is W2 transpose into the delta value, right? Use this to calculate the delta 1. So what is the delta 1? Delta 1 has to be, you have to use the previous formula that is used in the delta rules, right, to calculate this. So that is the y1 dot star, it is 1 minus y1, again dot star, the error of this layer, that is E1. Right. Using this delta 1, I have to update my weight. So for that reason, I have to calculate dW1. So change in the weight is equal to alpha multiply alpha with the delta 1 into the input, right? The input is equal to X. I have to take a transpose to match the matrix multiplication requirement. All right, so that's why it is the X dash. Then let us simply write the, therefore W1 is equal to, this is the weight update for the first set. So this is the old value W1 plus it is dW1. Update the first weight. All right, so that is done. Next, you see, I have to update my second weight as well. So that is dW2 is the change in the weights, right? So dW2 should be equal to, once again, the alpha value multiplied by the, I think the delta itself, right? So into, what is the input to this layer? If you remember, this is y1, right? And I'll take a transpose to meet the requirements of matrix multiplication, right? So then W2 is equal to W2 plus dW2. Okay, you can see that the uh, both the weights get updated over here, right? So I'll do an end and another end to finish the program, the function itself. Okay, so this is the function which implements the back propagation, and it also incorporates the uh, cost entropy function to maintain the cost. All right. Okay, now let's proceed further and let's write the function to test this. All right, so I'll edit. I want to test this function. Okay, so test backprop CEF. It opens up a new window in the editor window, and there we'll write the program. Okay, so let's start with the standard commands to clear all the other variables, right? It's clear, close all, and CLC. Okay, now let us define the inputs first. So inputs is capital X equals to, give the same data. So it's 0, 0, 1. Then 1, 0, 1. Then we'll write 1, 1, 1. Then 0. That's the input vector. Then let's write the desired vector. So D is equal to 0, 0 means it is 0. Next data is 1, 0, so that is 1. Next is 1, 1, so that is 0. And last is 0, 1, that is 1. So this is the desired. All right, now let's, if you recall, the next step is to define the weights. So W1 is equal to, let me write, this is say 4.5 times random. I just want to random. So recall the size, 3 inputs, 4 neurons to be connected. So this has to be 4 comma 3. All right. So that's how we write these values. This is 4 comma 3 minus a 3.5. Then W2 is equal to 3.5 into rand. So recall the size. The second weights should be of size 1 cross 4, right? Because there is 1 neuron and 4 inputs to that neuron. So because of that, I can write, now this is 1 comma 4, right? I'll subtract a random number from that, maybe 2. Okay, so this defines the 2 weights, right? That is required. Now simply call the function so many times that is equal to the number of epochs. So let's go to the epoch case. So let me open a for loop for epochs equal to, let me say, it start from 1 goes to say 1000, right? Anyway, we already have seen that at least 1000 is required to see a clear cut output classification, right? So let's start with 1000. All right, later on we can increase if required. So call the function. The function call is the output w1 and w2 to be equal to, call the function. The function name is backprop CEF of, pass the values w1, w2, then x, then d. So this is being called 1000 times because 1000 is the number of epochs we are defining. This finishes the training part and I call the end for this for loop. Okay, once that is done, now I just have to test my neural network with by giving the inputs, and I should check whether I'm getting the proper classification or not, right? So let's do that. So there I just have to define n is equal to 4 data I am passing. So use a for loop for say j is equal to 1 and it goes, sorry, start from 1 and goes till capital N, right? So you have to select your input. So x is equal to capital X of j, comma all the columns, right? Take a transpose. Then once you give this x as input, you will be able to calculate the v1 first. So what is v1? v1 is equal to the w1 into x. All right. So v1 is given. Then you calculate the y1. y1 is equal to my sigmoid of v1. Once you have the y1 with us, you can calculate a partial output of the second layer, that's the output layer, which is v is equal to w2 into the past output, that is y1. and you get a y that is equal to my sigmoid of v, right? So since this is a loop, I can actually create a y of j itself, so that I accumulate all my outputs over here, and I end, then let's write v, not v, sorry, y. Okay, so this y gets printed out. So using the cost function, this is the code. Let us try to run this to see the output. Okay, let me save this first. Okay, let's run. So you can see that we were expecting 0101. With the 1000 number of iterations, we are getting this answer. Okay, it actually can be seen that this is much closer, right? In 1000 itself, I'm getting a very close answer. 0.00, 0.99, 0.00, and 0.999, right? So actually this is much closer than all our previous cases, right? So you can see that there is a lot of improvement, right, in the learning process, because weights are getting updated, or weight are being optimized quickly compared to the other methods. Okay, now let's go for 10,000 and let's run this. So you can see this is very close, right, up to 3 decimal places. If I increase by one more, I think I should get much closer answer. So let's try that. So this is 1 lakh iterations. So you can see you got the proper output, right? 0 1 0 1. So this result we never obtained so far, even after doing 1 crore iterations, right? In the all the previous cases, you can check that even if you do 1 crore iterations, we never reached 0 1 0 1 exactly. But this method is going to give you that. So that's the ultimate advantage of using what is called as a cost function rather than the other functions. So other functions are going to act like a basics for you, right? Now you learned in a step-by-step procedure how to improvise your machine learning things, right? So we started from SGD, right? Stochastic, the gradient descent, and now we are at cost, at a, what is called as the cost function, right? Which can be considered as one of the ultimate uh, methods to implement and improve our learning rules. Okay, now, um, okay, let's do one thing. Let us try to compare the cost functions. All right. So my intention is to uh, check, say, what is the, how good is a technique like this compared to maybe, right? Okay, let's try to compare two things now. So first thing, I want to write another code now, and my intention is I will implement two techniques of cost function. One is the sum of the squared errors, right? The squared errors, I'll take a sum. That's one technique. And I also want to improve the cross entropy. Just now we have implemented that. And I want to compare. Okay, straightforward. Let's do this and let's try to compare this now. Okay, I'll try to bring out a graph which compares, right, the two techniques, so that it becomes very clear for us, right, to understand which is good. Okay, all right, let's go to another uh, program now. So I'll go for edit. Let me call this as a, okay, let me write, okay, I'm trying to compare the cross entropy, right, versus, let's say I want to improve, okay, the sum of the squared error. So SSE, this is my, the name of the program. Okay, so it's CE, standing for cross entropy, uh, versus the SSE, sum of the squared errors. SSE is already implemented, so I don't have to write another function over there. Simply I can call it. Okay, that's why I'm comparing with that. All right. So it's not a function. I'm just writing a program to compare two functions. Both the functions are already written, so I don't have to write the separate functions again. Okay, I'll simply call them. But before that, let's close all, clear CLC. Okay, now let's start with that. So I'll define my input vector, that is x. Again, I'm trying to compare both methods by by implementing them for the XOR problem itself. All right, let's see. So x is equal to, let me write the same data set which we considered earlier. So this is 0, 0, 1. This is 1, 0, 1. Then 1, 1, 1. Then 1, 0. Then let's write D, the desired vector. So first class 0, 0, so 0, then 1, and 0. So let me define the weights now, right? I will define the weights. See, I'm comparing two different methods. So I'm expected to initialize the weights of both the techniques identical, right? Otherwise, there is no meaning in comparison. Okay, so whatever is the W1 should be the same W1 for the second method, right? Whatever is the W2 for first method should be initialized with the same W2 for the second method, all right? So I will start from there. So let me define, so I'll call it as W11. W1 of the first method is W1. Okay, we'll define that as a say 2.5 times rand of the first one has the size of 4, 3 minus 1.5. Then W, it is W2. So the first one suggests that which method it is, W1 2. So it's a second layer of the first neural network is say 3.5 into, this is rand of one neuron with the 4 inputs. Okay, this minus say 3. Let's initialize this. Now the same weights have to be assigned to the other method as well. So W21 is equal to, I'll simply make W11. So that's, it means it is same, right? And I'll call say W22, that is also equal to W12. So first layers of both neural networks are same weights, and second layers are also defined with the same similar weights, right? W22 is equal to W12. Then we need a space to hold the errors now. So only when we have the errors, we can actually do something. So I'll start with what is called as the number of epochs. Epochs equal to, say, I start with 1000. So when I do 1000, let's see. The error vector E1 for the first method is equal to, initialize with zeros. Okay, zeros. How many zeros? What's the size? It is the epoch, because every epoch will give you error, right? So many epochs, comma 1, right? So E2 is equal to, let's define E1 itself, because E1 is already having so many zeros. All right. So now let's go for a for loop. For I is equal to, starting from 1 till epoch. So many epochs I'm trying to perform. Okay, so for I is equal to 1 to epoch. Calculate the weights, right? Using both the methods. First one is W11. The second weight is W12. First method, first weight, first method, second weight is equal to, you see, I have to call two functions, right? So the first function is the back propagation of CEF, the same method I'm going to call. So this is back prop CEF of, pass the same weights W11, W12, this is X, D. This actually updates the weights W11, W12 using this. Okay, also I want to check the SSE method. I think SSE was implemented in the simple back propagation. Let me just check the code once. See this one, I guess, back prop XOR. Yeah, okay, let's do this. Back prop XOR. This is a function which I'm trying to use now. So this is W21 comma W22 is equal to, I'm comparing with the, so the back prop XOR. Pass the required weights W21, W22, X, D. So we know that it actually trains. So now you'll see every time I train, I need to calculate the error, right? So so the storing of the partial error, let's define a vector, so some value that is ES1 for the first method. So let me say ES1 equal to 0, and ES2, let me also initialize this with 0. ES1, ES2, both are 0, 0. Okay, then I know that I have 4 inputs, so n equal to 4, 4 classes. Then, sorry, 4 inputs, 2 classes. I'll define, say, for j is equal to 1 to n. For j is equal to 1 to n, x should be equal to capital X of the j, comma, all the column, take a transpose. Then you tell the machine what is the required value. So d is equal to d of j d is equal to d of j. So once this is given, we can calculate the values v1, and the v1 is equal to, first method is w11 into the x. Okay, so we have to do this twice, right, so that we can calculate. See, the first technique is going to generate the error straightforward, uh, right, but the second method I need to do it in a different way. That's why we are writing the code over here in this fashion. So v1 is equal to w11 into x, then calculate the y1 partial, the output of the first layer is nothing but my sigmoid of v1, right, that is y1. Then v is equal to w12 into y1, then y is equal to my sigmoid of v. Okay, this is how you calculate the output of the first this thing. So let me calculate the errors of both layers now. So ES1 has to be equal to ES1 should add this with the squared term, right? So what is the squared term? D minus y the whole square. So, okay, so raise it to the power 2. That's the first one. Similarly, I'll calculate the once again v1, y1, etc. Okay, so this is the v1 of the second layer. Anyway, v1 is already used, so that doesn't matter. So v1 is equal to w21 into x, and calculate y1 is equal to my sigmoid of, there is a v1, so this becomes, I have to use a v1 itself, right? Then calculate a v is equal to w22, multiply that with the y1, okay, and calculate a y, final output is equal to my sigmoid value of v. Then ES2 should be equal to the ES2 of the previous value plus the same difference. Okay, so that is d minus power 2. So we calculated this. So end the loop which we had started just now, and now I need to calculate the error. So E1 of the particular epoch, right? I think it's sorry, it's not epoch, it is I. I holds the count, so E1 of I is equal to whatever ES1 you got so far, divide that by the n, that is 4. Okay, similarly E2 of I has to be, this is for the second method, so this has to be ES2, right, divide that by n. All right, then I'll end this. So this was the first for loop which we opened up, it ends up here. All right, now I should go for the plot. Okay, so that is plot. I'll call both the plots on the same graph. Okay, so that is, I want to plot E1, right, comma, let me specify the color, maybe I just want to red color. I'll hold on plot say E2 is the name, and say green color, and legend. See, the first plot is for E1. E1 stands for the cross entropy. Okay, this is the cross entropy. I have to put a single quote as it is a character array. All right, so comma, I know that my second graph is the SSE, sum of the squared error. Okay, so anyway, we can add the X label, Y label, that's fine. All right, so let's try to run this and check whether this is going to give you the answer. Yeah, right, you can see that the cross entropy is coming very closer, right? So it actually is very steep, and it actually see, the y-axis is actually error. So let me do one thing, let me add the X label and Y label as well, so that this becomes easy for us to trace out what is happening. Okay, so I'll add the X label now. So the X label is nothing but the epochs. Epochs versus say the Y label has to be, it's the average error. Okay, so this is let's run this once again. Right now you can see that the epochs are 1000 to this. As the epoch increases, you can see the SSE method is still having some error, right? Right, you can see here, whereas this becomes error becomes 0, right, very quickly within 100 epochs. You can see that error is very close to 0, right? Y is equal to 0.0008, whereas at the same time this is somewhere here. You can see error is 0.09, right? When the iterations are around say 45 50 itself, the cross entropy technique brings the error to 0, whereas, right, the other method is still having, right, some amount of error, right? So this gives you a very clear cut idea that how the two methods of what you call uh, the entropy function, one using entropy function, the other one using the sum of the squared errors, right, how they are different, right, and how the cross entropy is much better compared to them, right? This is what we are going to understand, right, when we look at this kind of problems. Okay, all right. Now let's move on to the next topic, right? That is, will bring the will bring the neural network classification into picture. So far we were looking only at the simple classes of XOR problem. Now we'll look at other types as well. Okay, so this is neural network and the classifications. Right. So in the previous topics, we understood the primary machine learning, and we also understood that it requires supervised learning, right? And we could do the classification, regression, etc. Right? Say neural network basically is a technique which is capable of performing classification as well as regression. Okay. Now, the first type of classification that we are going to look here is, right, called as a binary classification. So, as the name suggests, binary has only two classes. This is what we already had been discussing so far, but you see, we never use the term as binary. Okay. So, the binary classification is a type of uh, classification where the neural network requires only single output node, right? So what do you mean by a binary classification, right? It means one or single output node, right, that is sufficient for the neural network, right? So this is just because input data can be classified by the output value which is either greater than or lesser than a threshold. So set some threshold, say 0.5. If I set the threshold as 0.5, any output which is greater than 0.5 will be set as 1. Any output value which is lesser than 0.5, you can set it to 0. So you have two classes like 0 and 1. So when you have two values 0 and 1, it is a binary, right? Binary representation. So we call that kind of classes as a binary classes. So the XOR problem which we had been considering so far, right, throughout our discussion is actually a binary classification problem. Okay, right, but we never use the term, but now since we are looking at the varieties of the classification problems, the first one, which is the simplest one, and we already have been using this since long time. That's why we will call it as a binary classification. All right. So if you use a sigmoid function as an activation function, right, of the output node, so data can be classified by whether the output is, right, the greater than 0.5 or lesser than 0.5, right. It is obvious because my output is always between 0.5, sorry, 0 and 1. Sigmoid is between 0 and 1, right. So either it becomes 0, 1 or 0 depending upon some threshold value. So let us look at a binary classification problem. So it is always not expected that your output should be 0 or 1. It can be any other class. Let me show you one diagram, okay? Wherein I have the two classes are clearly visible, but by default the classes have not been named as 0 and 1 like the XOR problem. Okay, you can see here. So see, this is, let us say the data set is like this. Whatever data set you see, it's like this. So it's very clear that I have two classes. The first class is made up of all triangles and the second one is made up of all circles. So we can assign, okay, circles as zeros and the triangles to class ones, right? So I have to define a boundary between them so that you can classify the circles and the triangles, right? Whenever a randomly given data is selected, it should classify whether the data belongs to class 1 or class 0. So since you have only two classes here, this is very clearly a binary classification problem. So how do we define this data now? So the data, you can define this data set in the following fashion. How do you generate the training data? So the data set which belongs to a binary classification is what is called as training data of binary classification. So let's look at the data now, how the data is going to look like. Okay, so this is, so for this kind of training, let's say the data is going to look like this, right? See, I just have to add which class it belongs to, right? I just have to do that. So that means I have to add a triangle or circle at the end, right? So this is how it's going to look like. So this was a requirement and we finished that, right? Now let us try to construct the required neural network. Now the number of input nodes should be equal to the number of input parameters, right? This is our first step in building the neural network. So we are just trying to recall what we have done, but I'm going to write some steps here because these steps will remain same for any neural network that you are trying to build, okay? So this is to build the right. First, you need to select the number of input nodes. Okay, so this is the number of input nodes equal to the number of input parameters. Right. So as the input of this particular example consists of two parameters, my neural network employs two input nodes. That's what I understand from this point. Okay, right. Once I know how many input nodes are to be selected, we need the output node, right? So number of output nodes basically depends upon, right, the how many groups are to be addressed. If you have two groups, you just need one node. Okay, right. Number of output node equal to 1. This is obviously because it is a binary, right? It's a binary classification. All right. Then let's say I want to implement what do you call as the hidden layer. Hidden layer size is random, right? You can give any number of hidden layers, but ideally speaking, how many input data you have, right? If you are using single hidden layer, this is the ideal data. Again, you can change, lesser than that will also work, no issue. But you see, I have 4 inputs to give, correct? I have 4 different inputs. So I make sure that I have at least four neurons in the hidden layer. Okay, so I'll just write let, okay, number of neurons or number of nodes in the hidden layer be equal to 4, right? So just remember why I chose 4, because the capital N equal to 4 here. You can increase, you can decrease, still it may work, right? Lesser than 2 may not work, okay? At least 2 or more than that will work, but it is good to have N equal to the number of data, the number of classes you have. Sorry, number of data points you have, not classes, number of data points you have. I have 4 data points, so I declared it as a 4, right? And you need to choose the activation function. So how to choose the activation function? That the choosing activation function is directly dependent on what is the range of your output. Output I'm expecting between 0 to 1, right? So output range 0 to 1. So one such activation function which gives you 0 and 1 in the output, right, is nothing but the sigmoid. Right, so we are using this. So according to this particular concept, what we use to decide the neural network architecture. So our neural network that needs to be used for this kind of training data looks like this. Okay, the standard one which we use so far is also very similar to this itself. Okay, so what is the output that we are trying to expect from this? It is very simple. From this neural network, the output will look like this. Just see. It will be a class 0 if, sorry, I'll just write in a different place. So the output is going to be class 0, right, for circular. Okay, and the class 1 if it is a triangle, right? Actually, so instead of giving the input data in the previously specified format, because entering a triangle and circle to my computer is difficult, right? So characters are not preferred, numbers are preferred. So the modified input data. Okay, so if you have classes like circle, triangle, or any other like ABC, etc., right, it is always preferred to convert them into the numbers, right? So when you do that, my training data is going to look like this. Okay, so this is obvious because you see that the classes are replaced by ones and zeros instead of having triangles and circles. So handling the triangle circles will become pretty difficult for this the MATLAB. Okay, or even for any other programming language, specifying a triangle over there is very difficult. Okay, so we use a neural network. The binary classification of the neural network usually adopts the cross entropy function of the previous equation for training, right? So always we don't have to do all of them, right? But it is beneficiary if for the performance and the implementation process if you go for the cross entropy function, right? So let us try to write down the learning process. Okay, so let's quickly write this. This is going to be the ultimate point to be remembered for any algorithm where your intention is to bring the binary classification or write a code for the binary classification. Okay, so or procedure for binary classification. Step number one, right? The binary classification artificial neural network has how many nodes? Only one node, right? Has only one node for the output layer, right? Always, since it is binary, so you need to use the sigmoid. Use the sigmoid function as the activation function. All right, that's the step number one. Then let's go to the step number two. So you need to switch the class titles of the training data into the numbers using a maximum and the minimum possible values of the sigmoid function. So this is the step number two. All right. Switch the class titles of the training data into numbers using the max as well as the minimum values of the sigmoid function. So like we did earlier, so that is class triangle, assign it to number one. Say if you want, say class circle, right? So I'll just color it, so saying that this is not just this thing, it's a color. Okay, I'm coloring this, so it's not just a circle, uh, cir color circle. I just want to write it as this. All right, the next thing that I want to do here is step number three. So this is to initialize the weights of the artificial neural network, right? So you can actually put maybe some random values or smaller values, whatever, as per the convenience you can do this, right? So in the next step, that is step number 4, what I'm going to do, I have to enter the input, right? Enter the training data, enter the training data to the ANN, right? Calculate the output. So what is the output? Output is nothing but the y. Calculate the output y, right? Then error and the delta value. So y is there. How do you calculate E? E is equal to d minus y, and the d del. So that's a delta. Sorry, right? So it's delta is equal to error. So this is for the output. So once it is done for the output, step number 5, you propagate the output delta value backwards and calculate the deltas of subsequent layers, right? How do you calculate that? That is EK is equal to W transpose into the delta. Then the delta of the kth layer can be simply phi dash of Vk into Ek, right? So this step number 5 has to be repeated until you reach you finish all the hidden layers, right? So repeat step number 5 to finish all the hidden layers. Then step number 7, right? Adjust the weights of the neural network, or actually update the weights. So first calculating delta Wij is equal to alpha into the delta I, alpha into delta I into xj, right? Then Wij is equal to Wij, the old value, plus delta Wij, right? So repeat these steps. Let me write 8. So repeat the step number 4 till step number 7 for all the training data, that is 8. And the last step will be repeat the 4 to step number 8, step number 4 to step number 8, right, until the ANN gets trained properly. So until we train the neural network properly, the step number 4 till step number 8 needs to be repeated. So once this is finished, we can say that so many epochs which you have decided, they are complete, because the 4 to 8 once means one epoch. So 4 to 8 is repeated several times means you are performing any number of epochs which you have defined inside your algorithm. So we expect that the machine learns properly, right, once you do till there.